Last class we showed that a function can be represented by its Taylor or Maclaurin series using the formula centered about x equals 0, and we also looked at what would happen if it was not centered about x equals 0. This is very cumbersome to use, so what we want to do in this lesson is talk about ways to avoid using this complicated formula by just using previous series. So let's start with our first example. Let's assume you have the following series. F of x is equal to 1 over 1 minus x. Now, if you remember what we had to do before, you would have had to take multiple derivatives, plugged in 0, plug into the formula, and hopefully you can find a pattern. That's very difficult. However, recall the following fact. Recall that for a geometric series, which has the form sigma n equals 0 to infinity a times r to the n, which is, if you expand it out, looks like a, plus a times r, plus a times r squared, plus a times r cubed, plus on to infinity, there's a formula to find the sum of a convergent infinite geometric series, and it was this, a over 1 minus r, provided that the absolute value of r was less than 1. So if we look at this series, it very much has the same form where a is 1 and x is r. So without doing any work, I can tell you that f of x can be represented by its power series as sigma n equals 0 to infinity, a is 1, and then r is x to the n. And if you write it out, it looks like this, 1 plus x squared plus x cubed plus dot dot dot. What's remarkable is this very simple series actually represents the function above. What's easy about this is the radius of convergence and the interval of convergence is not in question. Because we know that r was x, we can say that the absolute value of x has to be less than 1. So that tells you right away that the endpoints are negative 1 and 1. We know for a geometric series that it can't equal to 1, so we know that it has to be open, open. Very simple. Let's look at a second example and just change things up slightly. Let's say your function instead was 1 over 1 plus x. Well, that doesn't quite have the right form until we do the following. We change it to 1 over 1 minus negative x. So you can clearly see in this example that a is still 1 and your r this time is negative x. So if we plug it into the formula for a geometric series, f of x is equal to sigma n equals 0 to infinity negative x to the n. Okay, which in this class it's preferable that we simplify it as sigma n equals 0 to infinity and break it up as negative 1 to the n, x to the n. And you can see it's very much just the previous series except for the SIGNs alternate. Let's look at a third example. All of these are actually from the table of common Maclaurin series we've looked at in class. So let's change it just slightly. What if it's 1 over 1 plus x squared? Well, we can write this as sigma n equals 0 to infinity. What is a in this case? It's 1, so I'm not going to write that down. And r in this case is negative x squared to the n. And again, you can break that up as sigma n equals 0 to infinity, pull out the negative 1 to the n, then x to the 2n. And if you write it out, you just get 1 minus x squared plus x to the 4th, so on and so forth. The interval convergence is still just as easy because in this situation, absolute value of r is absolute value of negative x has to be less than 1, and so it's still negative 1 and 1, open, open. Similarly here, the absolute value of negative x squared is less than 1, and so it's negative 1 and 1, also open, open. Now don't feel restricted by what you can have as a. So for example, it can be a variable. Let's say you have the following. F of x is equal to x over 1 plus 2x. Okay? You can still do what we did before, recognizing that a in this case is x, and that r in this case is negative 2x. So the power series for this, without going through all the derivatives and finding the pattern, is sigma n equals 0 to infinity x times negative 2x to the n. If you want to simplify that, you can write it as sigma n equals 0 to infinity. Pull out the negative, so there's a negative 1 to the n. Now there's a 2 to the n, and there's an x to the n, but also an x to the 1, so that should be x to the n plus 1. Interval convergence in this case, absolute value of r, which is absolute value of 2x, has to be less than 1. That tells me that absolute value of x has to be less than 1/2, so it's going to go from negative 1/2 to 1/2, open, open. Let's take a look at a slightly more complicated example, for example 5. Let's say the function we give you is 3x minus 1 all over x squared minus 1. So you might be tempted to do the following, which is going to be wrong, but just bear with me, so you don't need to write this down. 3x minus 1, and then you can maybe pull out the negative and switch the bottom. And then you might say, well, the power series representation of that obviously is sigma n equals 0 to infinity. Your a is negative 3x minus 1, and then your r is x squared, so it's going to go x squared to the n. The problem with that is here, because if you pull out a 3, this is really x minus 1/3. The issue is, in order for geometric series to work, it needs to be centered about x equals 0 the way we've been doing it. Well, this factor is centered at x equal to 1/3, and this factor is centered at x equal to 0. So they kind of have different centers, which actually doesn't make sense. So we need another. If you think back, one of the things that people will notice that you can factor this into x plus 1 and then x minus 1 on the bottom. And you can break this up using partial fraction decomposition to look like this: 2 over x plus 1 minus 1 over x minus 1. That's the exercise will be left to you to figure out. So now let's look at each piece. So I have the 2 over x plus 1. If I write that out, a is obviously 2, and you should switch it so it's 1 plus x, so it's in the correct form. In this following situation, then our sigma form is sigma n equals 0 to infinity, a is 2, and then we have negative x to the n, which again you can write as 2, negative 1 to the n, x to the n, from n equals 0 to infinity. Let's look at the second term. The second term looks like this: 1 over, and if I switch it actually, so let me pull out a negative, 1 minus x. Okay, so working with this using the geometric series form, you get n equals 0 to infinity. Negative 1 is your a, and then it's x to the n. You can just totally pull out that negative, so I'm left with negative n equals 0 to infinity, x to the n. The problem is, if I'm going to combine this jobby with this jobby, that's actually not a power series, because the power series has to have the following form. It has to have sigma a sub n x to the n. So I need to figure out a sub n. The easiest thing to do in combining these is really just to pull out that x to the n. So you get sigma n equals 0 to infinity, something times x to the n. Well, how do we do that? We just take the coefficients, which is 2 times negative 1 to the n, and then here you actually have a negative 1 to the n. So this would be your final answer, where this jobby here is your a sub n. Let's take a look at a minor detail which might trip you up. Is let's assume you have the following situation. Let's assume you have x squared all over 2 plus 3x. Well, what's the issue here? The issue here is this 2. In order for it to have a correct form, this has to be a 1. So the easiest remedy to that is just divide every single term by 2. So then the form we'll have is x squared over 2 all over 1 minus negative 3x over 2. So you can clearly see, here's your a, and here's your r. So if I plug it into the geometric series form, it's going to be sigma n equals 0 to infinity, x squared over 2 times negative 3x over 2 to the n. Now simplifying that requires a little bit of algebra, so we'll go sigma n equals 0 to infinity. Obviously I have the negative 1 to the n. I have actually also a 3 to the n if you go ahead and distribute this n through every term in here. So I have a 3 to the n, and the x powers to the n, but don't forget there's this squared, so it's x to the n plus 2. All over, now this 2 has a power to the n, but there's also this 2 to the first power, so 2 to the n plus 1. One of the last things we'll explore is what if you have a fairly simple series like 1 over 1 minus 2x, but I want to center it not about x equals 0, but I want to center it about somewhere else, say about x equals 3. It seems very limiting to make sure everything is centered about x equals 0. So the approach we're going to do with this is we're actually going to use a method similar to completing the square. Now if it's centered at x equals 3, that tells me I need terms that look like x minus 3 to the n. Well, how am I going to create that? I'm just going to actually add it in. So I'm going to create a 2x minus 3 in parentheses. Okay? But if you look at what we've done, we've actually changed the equation a bit, because here's what I have. I have 1 minus 2x, which is the same as the original equation, but now I have a plus 6. So to even things out, just like you would in completing the square, you have to subtract 6. and then I'm back to the original equation. So if we simplify this, you get 1 over negative 5 minus 2x minus 3. Again, the issue here is this term needs to be a 1, so we're going to go ahead and divide every single term by negative 5. And the series rewritten, or the function rewritten, looks like negative 1/5 over 1 plus 2/5 x minus 3. So in sigma form, this looks like sigma n equals 0 to infinity. Our a is negative 1/5, and our r is negative 2/5, parentheses, x minus 3, all to the n power. And to see how that gets simplified, let's just work out the algebra. Negative 1/5 you can pull out or you can leave in. It doesn't really matter. I'll go ahead and at least pull this negative out. On the top, I have this negative sign, which is raised to the n power, so it's going to have a negative 1 to the n. I'm going to have a 2 to the n all over, and I got a 5 to the n here, but a 5 to the 1 there, so 5 to the n plus 1, and then x minus 3 to the n. And that's your power series if you want to shift it over.